I feel like I could probably get started. Like probably most people are here already. So welcome back, everyone. Uh, if this is your first meeting, thanks for coming. Hopefully it'll be easy enough to follow along with. This is kind of like a almost a tradition at this point to do a Fibonacci related topic as the first meeting of the semester. We've done many. I don't think we did last semester, but we have many semesters. Um, and actually we've done this Fibonacci heaps meeting before, so hopefully it's your first time. But basically Fibonacci heaps are like a data structure type of priority queue for that's really good for like large data sets basically because there's a lot of inefficiencies. But I think it's interesting data structure because you can kind of go through it and see like building on like different iterations of like previous versions. Um, And it seems like reasonable that someone could have come up with this. It's not like super complicated. So I feel like it's like a good hands-on example. Um, so yeah, I'm gonna first give some background about priority queues, then talk about binomial heaps, which is kind of like a stepping stone in between um, basic binary heaps and Fibonacci heaps, um, and then get to Fibonacci heaps. So who here has taken CS225 already? Okay, about half. Yeah. So this is review if you have. If not, it'll be review when you get to 225. So basically, a priority queue is like trying to a data structure for um, putting things in order, basically. So like you want to do the highest priority thing, so it's used in like a lot of different things, like scheduling as an example. But like you want to do the highest priority thing right away. So a priority queue is basically the abstract idea of like put things in order. Um, with these basic operations, insert, find min, delete min, and decrease key. So, okay, so there's like, you can think of it as like high priority, like you want to get the high priority thing, which is like why it's called priority queues, but most literature uses minimum priority. So I'm going to be using minimum the whole time, so so it's not confusing. So the minimum is like the highest priority, but it's the minimum value, whatever. Um, Yeah, so you could think like one implementation would be like a sorted list, and then you just take the first element because it's like that's the smallest. But then you're doing a lot of extra work to keep the rest of the list sorted, which you don't need because you only are ever curious about what's the smallest value. So the first iteration on improving that is binary heaps, which is a binary tree that has two properties. The first property is that all children have a greater value than their parent, and we call this the heap property. So then automatically the smallest value is the root of the tree because it just gets larger the deeper you go. Um, and then the second property is that the tree is complete, which if you don't remember or have never learned, just means that it's like goes in order. So like if we look at this tree, basically you fill each level from left to right, and left to right is arbitrary, but like the next value we would add it here in this open spot, and then the next one here. So the reason we do this is so that it can fit into an array nicely, because arrays are very fast and like the hardware level. So like we would have like this is the first element of the array, then this is the second, then the third, fourth, fifth, and you just like go down each row. Um, and that makes it like very fast, basically. Um, and yeah, like I said, the root element is just the smallest element. So you can just get that like instantly. So if we think about insert, the first function that we need for this to be a priority queue, we just add it to the end of the array, which is just the first open space in the tree. And then that that satisfies the property that it's complete, right? You're just adding it to the end. But then it invalidates the heap property that it gets larger the deeper you go. Because 10 is smaller than 19. So then what you do basically to fix that is you just bubble it up. So we bubble up 10, swapping it with its parent until its parent is actually smaller. So 19 and 15 were both larger than 10, so we swapped it. But then it gets to the point where 7 is smaller, so 10 is in a good place. And now the heap property is fixed. Yeah, and because the height of the tree is you at most have to swap the new value all the way up to be the new root. The height of the tree is log n, so the worst case runtime of insert is big O of log n. Find minimum is just the root, so that's 3. Delete the minimum is another, it's a little bit tricky, because if we just get rid of 7, then like what's the new root? Is it 8 or 15? If we make it 8 or 15, then it's like becomes unbalanced and wonky. So what we do is we swap the last element in our array, and bring it to the first element, swap it with the root. But then, so that maintains the complete property, but then we have to again fix the heap property, which we do basically the same as insert, and just bubble it down until it's in a good position. Now, can anyone tell me why we, from here to here, why we switched with 8 instead of 15? Yeah.
The top of the tree is small.
Right. Yeah, and then 15 is greater than 8, so if we swapped it, then it would still be invalid. And just like insert, so log in, because worst case, you're gonna swap to the leaves of the tree. And decrease key, which I don't know, it's kind of like an arbitrary function. I don't know if it's super useful, and there might be other functions that are useful additionally, but basically it ends up being basically the same as insert, just like make it smaller and then bubble it up. So that's kind of in summary, everything is log n except for find min, which is free. And then Fibonacci heap, I'm claiming, is going to be constant time, big O constant for pretty much everything except for delete min. So are there any questions so far? Okay, hopefully review. And now where it starts to get interesting is binomial heaps, which is, I don't know if they're really useful for anything, but it's kind of like a logical stepping stone before Fibonacci heaps. So yeah, the idea is like well, there's 2 ideas. What if we use more than one tree? So a binary heap is like just a priority queue implemented with one tree, but we could use more than one tree. We could use a forest of trees. And then each binomial tree in the forest of order k has k children that are themselves binomial trees of decreasing order. So k minus 1, k minus 2, and so on. And in our forest, there can be at most one binomial tree of each order. So like these are the rules of like what a binomial tree is, and we can only have at most one binomial tree of each order. But then these are properties. Given this construction of trees, each level in a tree of order k has k choose L nodes. And that's why it's called binomial trees, because this is the binomial coefficient. And then another property of that, this is like, you can get this if you draw out the like Pascal's triangle, whatever. It's really important, but this is just another property. Each tree of order k has 2 to the k nodes. And then a result of that is that the largest degree is bounded by O log n. Which is going to be useful later when we look at Fibonacci heaps. That's kind of confusing, but it's very helpful to look at this picture, where each node is labeled with its degree, and you can see like this blue set of nodes here has degree 2, and it just is like, is this degree 2 tree? And then if you think about Pascal's triangle, which is where like the binomial coefficients come from. And this comes from, if you're not familiar, like if you expand like some binomial, like this cubed ends up giving you like x1 x cubed plus 3x squared plus 3x plus 1. And then these coefficients match these the number of nodes at each level. So like 1, 3, 3, 1. It's kind of interesting, this relationship between binomials, and that's why it's called the binomial heap. And you can keep expanding this more and more and more, and it matches this Pascal's triangle. And importantly, it has that the exponential bound. The largest tree is bounded by a big O log n, which becomes useful for Fibonacci heaps. And interestingly, if you combine 2 degree D trees, you get a degree D plus 1 tree. So like these are each degree 2, and you combine them and it's a degree 3. Yeah, and then so this is as a improvement from binary heaps. Binomial heaps can have insert and O of 1 time. By just like when you insert, you just like make a new tree with just that value. Is like kind of a hacky way to just like you're like inserting it, but you're just like making a new tree. And I don't want to get into the details of it because it's basically like Fibonacci heaps and not really interesting. But with amortized analysis, you can convince yourself that it's constant time to do insert. And I'm going to talk more about amortized analysis in much more detail later. So it's not really important, but my point basically is binomial heaps are a little bit better than binary heaps and in this abstract way. Any questions about that? It's kind of disconnected from everything. It doesn't seem important yet, but does it make sense? Yeah.
Also a disconnected question, but what do you use to make the slides?
Thank you. It's LaTeX,
Oh.
and
I really
then
think slide is awesome.
yeah, and then the specific package for all the drawings is called TICZ or something. I don't know. That's actually what you call it, but yeah, TIKZ. Yeah.
You only insert new trees off the roots.
So, like this collection of 4 trees is a binomial heap, right? There's multiple trees. And like, if we were to insert, I mean, so these numbers are the degree, so it's like, I don't know, they're not like the actual values, but like if we were to insert a new value, we would just make a new tree that is just a root node, not connected to any of these other trees. So then it does get a little bit like, I said here that there can be at most 1 binomial tree for each order. So if you create a new tree that's just a root, that's order 0, and we already have one of order 0. So then it's like you would like combine them and like merge trees and like do some accounting, and it's kind of complicated. And we're gonna see something similar when we look at Fibonacci heaps. Yeah, but that's why you need the amortized analysis to have it be constant, because it's a little bit more than just creating a tree. Yes.
Oh, I'm gonna ask, well, so, can you go back 1 slide to the, or 2 slides again? So, where exactly are like the binomial coefficients of this? Because I just like didn't.
Sure. So, I mean, these are the binomial things, right? So then if you look at each level, that's where it comes from. So like, if we look at this tree, level 0 has 1, and then 3,
Oh.
and then
okay.
3,
I see.
and then 1, and 1,
Okay.
2,
Yeah.
1.
I'm noticing like if you add an extra node, for example, or like these all seem like complete kind of like if you took away a node, I feel like the pattern is really old. Or I don't know if my point is here, but if you have like a normal heap, like the bottom layer is like sometimes not fully complete because like the bottom layer is like half of them done and half of them is done. Like what happens if you take a node out of it? It's like,
Yeah, so the completeness property that I was talking about,
yeah,
that's only for binary heaps.
okay.
And that's so that it can fit nicely into an array. But this does not fit nicely into an array. So yeah, the same kind of thing doesn't really apply. Like, this would probably be implemented with lots of pointers. Yeah, a lot of accounting, and that would be really annoying. Does that answer your question?
Yeah.
Okay, cool.
Well, we had to traverse down Beach Street.
Yeah. Yeah. Or you could probably just keep track of the minimum. And then like if you end up with a new tree, then you do just have to compare, like, is the new tree have a smaller minimum than the other ones?
Well, after you get rid of that, then you have to find the next one.
Yeah, but like if you have like some, like if we have, I don't know, like if we say 0 is the minimum, we have a pointer pointing to that. Then if we insert a new value, that's -1, I don't know. Then we could just like, when we're inserting that new value, we only have to compare between what was the minimum and what is the new minimum. So you wouldn't need to traverse all of them. And that's actually, that's the same in Fibonacci heaps too. We're gonna see that again in a few minutes. Okay, so this is like the main event, Fibonacci heaps. It's a binomial heap where we like reduce restrictions. We like make a bunch of restrictions, and then we're gonna get into the details of like how to actually manage the accounting of everything and how it ends up giving us good runtimes. So it can have more than one tree of any degree. So the thing I was talking about like when you insert, you just create a new root. And that could potentially give problems because if you already have a single root tree, you would need to like combine because of the restriction that each tree needs to have like distinct degree. But in Fibonacci heaps, it doesn't matter. You can just like insert and create a new tree, insert, create a new tree. So you could just have like as many new trees as you want. And it's basically just like a random collection of values, which is kind of surprising that we can get actually a useful data structure with something so lax. But we're gonna see the details of that. So we can also remove at most one child from each node. Like so, and then you mark nodes that have had a child removed. So like if we look at this to match the binomial coefficient and like match the structure, it's a very specific structure, like you were mentioning. If you were to remove any one of these nodes, it wouldn't be a binomial tree anymore. So then that's like kind of gets complicated. But in Fibonacci heaps, we don't care about that. We just say like, it's okay if it's not exactly a binary or a binomial tree, but we're gonna mark that it's wrong. For reasons that we'll see. I know I keep saying that. Yeah, but it's a very, very loose structure. And again, we're gonna use amortized analysis. So now I'm getting to actually amortized analysis. Basically, the idea of amortized analysis is when the work done by slow operations can be attributed evenly to a predictable number of fast operations. So sometimes you hear people talk about algorithms and say like, oh yeah, the worst case is O of n, but the average case is O n log n, something like that. So it's like, we only really think it's log n. That's different than amortized analysis. Because if you're looking at the average case, like that's probably what will happen. And so that's like, we think it's pretty good, but there could be a situation where actually it's really bad and maybe it's like just the user inputs just the right case that gives like a really slow runtime or something like that. Amortized analysis is more like, it's more predictable. It's like, if something is fast, that makes it gonna be slow later, you can like take advantage of that if you know how much slower it's gonna be later and then like redistribute the work. So more specifically, we create a potential method where we bank time in fast operations and cash out in slow operations. So if we make an equation for it, if we say there's some operation O and some the potential function phi, we look at the difference of that and kind of square everything off with this equation. So T actual of O is the actual time that some operation took. And T amortized of O is like the kind of made up time that we're sort of lying that this is how long it took. And the potential function over time, it's like if t actual though was like really fast, like for example, insert in the Fibonacci heap and binomial heap. When you insert, it's like too fast because like we're just like ignoring all of the consequences. We're like, we're just gonna make a new tree and make insert fast. So we're kind of screwing up like regularity in our Fibonacci heap and storing that benefit, storing it in the potential function. So I don't know. The way that I think about it, this might not be a really helpful drawing, but it feels like very intuitive to me to think about it in terms of like integrals of like, I don't know, if this is the amount of time the functions are taking, and then like all of a sudden you have some operation that takes a long time. What you can do is you can actually like this is the actual time that everything took, let's say. And then this new line is the like the lie time that we're saying is that the t amortized. Like if we say if this was really fast, it's like actually let's say it took a little bit extra time, just like give ourselves a little bit of padding. We're like building up the potential function. And then when it gets to something that's really long, we've already accumulated all of this banked time, basically, like you could think of that like integral. And you have stored up all of this extra time. So then when something really slow happens, we can say the potential function is just like gonna counteract that and use it up. So that it's like, I don't know, maybe not so bad. Yeah.
So how exactly do you like bank time?
Yeah, so it's not, you're not actually doing anything.
Oh, okay.
This is just like to make ourselves feel good that it's not so bad.
Oh, so you're just like saying on average, just like that?
Yeah.
Isn't it more like, you know, 1 out of every 3 operations is going to take much longer? And
Right.
in exchange for that, the other 2 operations are really short.
Yeah,
So it's not exactly an average in the sense that there's no probability involved, but if you know, if you think about the time per operation, it's still going to be, you know, like lower than the maximum
Yeah.
case and higher than the minimum
Yeah.
case.
it's kind of like a trick, like in big O, usually you don't really care about like the constant, right? And so like the difference between 1 and 2, we don't really care about. So if we can take this peak, like this really slow thing and like squish it down, and it would like, I don't know, like I'm just imagining like you squish this down and it like makes everything else raise up. Then it's like, then that makes all these 1s are actually 2s. So then it's like big O, we don't care, 1 versus 2, it's constant. So it's kind of like a counting trick to distribute the work to faster things.
Okay.
Any other questions? Cool. Yeah, when we cash out, the amortized time is smaller than the actual time and the potential function decreases. Which saying it's usually 0 is kind of, who cares? There's not actually any value stored anywhere that becomes 0. This is just like a argument to convince ourselves that it's fast. Okay, so then we're going to get a particular potential function for Fibonacci heaps, which again is not going to make sense until the algebra works out later. But we're going to say phi is t plus 2m, where t is the number of trees and m is the number of marked nodes. Which remember we mark node when we remove a node, we like mark its parent. Yeah, and it's arbitrary right now. Okay, so for insert, like I said, we just add a new tree to the heap. With the new node as a root, and maintain a pointer to the minimum element like we were talking about. And so if this new value is the new minimum, update the pointer, and that's constant time. So the minimum element is pointing at 5. Now this is an example Fibonacci heap with a few trees. We add 3. 3 is obviously less than 5, so we update the pointer, and that's insert. Find min is again constant time because we maintain a pointer to the minimum, so pretty trivial. And decrease key is, so first we decrease the key. Here 40 became 29, and if the new value maintains the heap property, we're done. But if not. Like, this is a new example, where we change it to 14. 14 is less than 23, so it doesn't, so we cut out this little subtree and it becomes a new tree. And then we have to mark 23. Because we removed one of the nodes. Yeah. So if the parent was unmarked, which was in this case, you just mark it and you're done. But if we were to remove 21 now, or 35, if we decrease 35 to 21, then 21 is less than 23, so we have to cut out 21 and 23 because it's marked. Because you can only, once it's marked, that means that like you can't remove another child without cutting it out, basically. So you cut out 21 and you cut out 23.
So is there a problem if we just like leave 23 there? Like, what's the problem with, why do we have to get rid of 23, like in that tree?
So, well, okay, so I mean. The thing that I said earlier about like one of the rules of Fibonacci heaps is when you remove a child, you mark the parent so
Oh,
that like you can only remove at most one child from each node.
okay,
And the reason why to do that, we're gonna, because it makes the numbers work out and it makes the like that lines up with the potential function for the amortization. Because you want to enforce, you want to like have some idea of what these trees look like. Like if you just cut out as much as you wanted, then like if it could, then you could get like arbitrary shaped trees. Which is not helpful. We want it to be like pretty regular.
okay,
In particular, so that it's like we can know that it grows exponentially.
Yeah.
Which we're gonna see is important so that it gets log n time. I don't know, that's not really a very satisfying answer.
I think we'll see like what's.
Yeah.
It's just organizing the information so that you can, run operations quickly, like the same way with with the binary heap, you don't want like small numbers right at the bottom of the tree. You want it organized so that you can find things.
Right.
Same idea.
Yeah, it's just a rule
Okay.
that we're enforcing so that it's easier properties later. So yeah, so if we cut out, this was 35 and we cut it out, and we also have to cut out the parent. So then the analysis, if let's just say, when you decrease key, there might be like a chain of like, you might have a bunch of mark nodes, so you cut one out, then cut its parent, then cut its parent, and you might cut a lot of parents. But let's just say in some operation, we cut out k nodes. That means we added k trees. So of all the nodes we cut, only the first was unmarked, right? Because then like everything was marked, and that's why we cut it out. So then just basically, this is just basically algebra, like the number of marked nodes changed by the number that we cut out and the one that there was. So the change in marked nodes is minus k plus 2. And then this was our random potential function that we picked that wasn't actually random. So we know how many cuts we made, how many trees we added, and we know the change in the marked nodes. So then we also get the change in the potential function. And we put, so k, we added k trees minus k plus 2 times 2 algebra minus k plus 4 is delta phi. So the amortized time is constant because so like we have a minus k in here, and the actual time it took was like just the time it took to cut out each of the trees. And kind of hand wavy, the constant lines up with the potential function, so it cancels out. Big O doesn't really matter. But yeah, we're cashing out on the potential function. Something took longer, but we're using some I don't know, money, whatever, some value that we stored up in the potential function. Any questions about that? Yeah, and the choice of making this algebra work out was, you know, that's how this potential function, how our choice of that came to be. So like, if you were making this data structure, you kind of would have looked at it and been like, okay, I want this to be constant time. Where can I pull from? So then we say that like, this took k time, so we would like to get a minus k out of the potential function. Then you would go and say like, okay, minus k. We create some heuristic based on the number of trees and the marked nodes and whatever. And so that's like kind of how you would come up with that potential function. Okay, so then delete min is kind of the most complicated operation. Because this is where we start enforcing more order. So you would cut out the minimum node, which is a root, and make its children roots of new trees. So if we're cutting out the minimum, which is 3, we get some new trees. And with D children, the operation is O of D, and O of D is, there's gonna be a little proof on this later. O of D is O of log n for a Fibonacci with n nodes. That's actually the crux of like the Fibonacci heap, which is, again, we're gonna get there. Yeah, so then we need to update the minimum pointer, which there might be n roots, right? Because if we just inserted each thing separately, we would just have like single node trees. So finding the minimum is worst case O of n. But we're gonna use the potential function again to smooth it out. This is a long operation, right? And these were all the inserts. They were fast operations, and we've been banking up time. So then we get to a long operation, and it's only long because we did a lot of inserts. So like the more inserts you do, the longer this is. So you can evenly distribute the work of how long it is right now to the inserts. Is the way that I think about it. Yeah, so we're doing cleanup that makes it, yeah, and then once we find them in once, then finding them in again is easy. Once there's more structure. So yeah, so I'm gonna assume the largest degree of any root is O of log n, and get to that later. So if we take this assumption, the largest degree of any root is O of log n, then we'll create an array of O log n to track trees of every possible degree. And then you just like go through each of the trees that you have and like put them into a bucket. So this is degree 0, this is degree 2, degree 1, and then we get a conflict of 2 degree 1 trees. But because these are binomial trees, more or less, when we add them together, it basically just like increases the degree by 1. So we added these 2 trees together. And then that's degree 2. So then there's another conflict. So we add those together. And it's degree 3. And then we keep going, more of the same, more conflicts, more combining. But then we end up with a pretty organized set of, we had a bunch of trees and now we have just a couple pretty much binomial trees. And I say pretty much because there might be some removed nodes that have been marked and whatever. Doesn't really matter. But we know based on the assumption from before that this like array of pointers is enough to fit these trees. And then we have a lot more structure, and there's like only log n values to check to see which one is the minimum.
So we're keeping track of the degree of each subtree so that we can merge them to create something that's sort of correctly filled out.
Yeah. Like there was no structure, it was just like a bunch of little trees, and then after this step, we create a lot of structure. So that even now, if we were to remove the minimum and then remove the minimum again, now there's much more structure. So it makes it faster on the next ones. Okay, so now, so how bad was that for us to do all that work? So we allocated the array and visit each of the m starting roots for log n plus m time, because log n is from the size of the array. And m is just some number. So then delta phi, the number of mark nodes didn't change. So delta phi is just the change in the number of trees. So just final minus initial change in the number of trees. So then from that, we can get the amortized runtime based on like the actual runtime was log n plus m and then amortized. And then if we do some algebra, it ends up with the m's cancel out. In the log n's, we can like ignore the constant because big O constant. So amortized accounting with this potential function, and again, this potential function being just the change in the number of trees, that again is like the other another consideration in the design of the potential function. You wanted to get a minus m in here so that it would cancel out, which is how you would go about designing a potential function like this. But yeah, delete is log m. Any questions about that? Okay, so then the final phase is find the minimum of the log n roots that remain in log n time. Which is just still log n. So the delete min full runtime is log n because each phase was at worst log n. Questions? Okay. Okay, so now this is like the really like, why is it even called Fibonacci heaps? Like we know about why it's called binomial heaps because those were binomial coefficients, but where does Fibonacci come in? First of all, does anybody have like any guesses? Like we've already seen kind of where the Fibonacci structure comes from. Yeah, do you have a guess?
Well, maybe it's just like when you like merge two trees or something, you get like, it's like follows the Fibonacci pattern or something. I don't know.
Yeah, because Fibonacci is just like adding up yeah. So then when we were combining trees in the combining phase, that's where the Fibonacci comes from, and that's how we can get, because we know how fast Fibonacci grows at the golden ratio asymptotically is like 1.6, which is, so we can get exponential growth, so we can know that it's log n. It's basically the shape of this proof. So let's focus on one tree with degree d and n nodes in total, and we want to show that the number of nodes in the tree with degree d is bounded by, or the degree is bounded by the log n of the number of nodes in the tree. So then this is kind of just like algebra, basically, like big O is like there's some constant that we're ignoring. So if we put the constant in and then do log rules in algebra, just rearrange, where A has to be greater than 1, which A in this case is the golden ratio because it's Fibonacci. Which isn't important yet, but I don't know, it's kind of interesting to see here. So yeah, to make the algebra work, we need some value greater than 1. And then we end up with a to the d is less than n. So we want to show that n grows exponentially with respect to d. In other words, if you have like if you look at the degree of the trees, increasing the degree of the tree just by like 1 or 2 increases the number of nodes it can hold by a lot. Okay, so to show this, that n grows exponentially with respect to d, let's go the other way and look for a lower bound on n for some given degree. So if we have a tree of degree 4, so there's more nodes kind of below here that's not showing. But when x3 was added, it must have been degree 2, right? Because if we think x0, x1, and x2 were all one tree, we merged x3 with x0 when x0 was degree 2, so x3 must have also been degree 2. And same thing for x4. So each node can have at least most one child removed. So x3 must now have degree at least one, right? Because it was two and now it's one. It could be one, it could be one or two, but at least one. And x4 is at least two, because when it merged with the subtree of 0, 1, 2, and 3, there were 3. And in general, the ith child must have degree at least I minus 2. And then we can use this observation about like the size of trees when they were merged to build up the minimum tree for each degree. So like these are the minimum trees of degree 0 and degrees 1, which is like obvious. You can't, it's almost meaningless to say that. It makes more sense when you start looking at larger trees. So for a tree of degree D, we can add a tree of degree D minus 2 as a child of degree of tree D minus 1. So so like this is a degree 4 tree, and I say it's the minimum because we've removed from it as many nodes as we can, and still have it classify as a degree 4 tree. And this is why we had the rule about like marking a node when you remove something, because if we could remove more from this, then it's no longer a minimum. So if we enforce a minimum and say that the size of this tree has to be some minimum, that's where we can say we know that this must have exponential growth. And interestingly, you get each of these trees from combining the other ones. So like this, if we take this whole tree here, that's the blue in this, right? And this 6, 7, 8 is this tree here. Like if you combine 2 trees, then you get the next one, which is like same as Fibonacci. And if you just like number all of these, you see it literally is Fibonacci numbers. And like I mentioned, the growth of Fibonacci approaches 1.6 asymptotically. So we know that the number of nodes in a tree is at least the Fibonacci golden ratio to the D. So large trees must be, it must grow exponentially, which is what we wanted. So then, because we know that if it grows exponentially, then we know that the Liebman takes the amount of time that we wanted it to based on the assumptions we we're making about the log n, because log is the inverse of exponential, right? So then we get basically what we wanted. Binomial heap improved insert by having the like constant time insertion. That was the one idea. And then the next idea was using Fibonacci numbers to force it to grow exponentially. So then we end up with something that's appears much better than a binary heap. However, the structure that we were enforcing for the binary heap at the beginning of like using an array, have it be a complete tree so we can use the array, is pretty much like that structure. We only could use that for binary heaps, and it was really good because arrays are really fast in hardware. But for binomial heaps and for Fibonacci heaps, there's no arrays, so we have to use pointers. There's a lot of accounting, right? They're like make that array and then like combine the trees. There's a lot of pointer updates, a lot of searching through a list of, even though it's log n, it's still extra work that you have to do of search through that list. And it's all pointers. And if you've taken an architecture class, you know that pointers are much, much slower than arrays, much. So there's like a lot of extra work that goes into Fibonacci heaps, a lot of accounting that actually makes them like pretty slow. There's so big, the big O constants are very large. So it's technically asymptotically better, but it's so much worse on the constant that it usually doesn't actually matter. So Fibonacci heaps aren't used very much because there's like tends to be pretty slow. The standard C++ implementation is not Fibonacci, and they're really concerned about performance. So maybe that tells you something. I did find some studies though that Fibonacci heaps are actually better when you use when you have a huge data set, because I mean asymptotically, eventually it should be better.
Well, they would have to be.
Yeah.
If you increase n enough, then you're
Right.
sort of making the constant insignificant.
Yeah. Yeah, but the size of in the research that I found, the size of the data set was like. Almost like you aren't gonna encounter it unless it's like a huge application, like. It's not, basically, it's not very useful. But technically, it's better. Yeah, so any questions about that?
How big are we talking? Numerically.
I don't know exactly numerically, but it was like, it was very large and it was. Still not even that much better. It was like. You might as well not spend all the time implementing the Fibonacci heap. Because
So is the technique of like, look what we did when we were proving the like complexity using like a potential function. Can that be applied to like other algorithms as well? I think it's just like a standard technique, so I think there's like a lot of algorithms that have like multiple different like, like, I guess like processes that can but slow and fast, or I was just curious about that.
yeah. Yeah, I mean, it definitely is very applicable to a lot of things, like in C++, the standard vector, or just like using an array that can resize, it's the same type of analysis.
Okay.
Because if you allocate memory and then fill up that memory, you need to, if you're still adding more to your vector, you need to reallocate.
Yeah.
And what they do is they double the array. And that doubling is like the amount of time spent reallocating is not, I mean, kind of is, but it's not actually random. And it's, in particular, you can like distribute the like amount of time it takes to reallocate to the additional inserts later on,
Yeah,
if that makes sense.
yeah,
Because like, yeah, if you allocate 100 more spaces and then insert 100 more times, you can sort of blame the extra insertions later. You can give them the blame for the slow
yeah,
allocation
that
earlier.
makes sense. Okay.
Yeah. Yeah, anything else? Sweet. Oh, yeah. Well, yeah, so thanks for coming, everyone. If anyone is interested in making a meeting, please reach out. We can help you. We can help you find a topic. I don't know. We think it's like a pretty important part of the club is like people making meetings because you learn a lot when you make them. Yeah. So, yeah, thanks for coming.
Is there a break teaser?
What?
Is there a break teaser?
There is not a brain teaser. I apologize.